videos. My name is Lou.
And I'm Anna.
We are your hosts today. This video presents an introduction to thermodynamics.
We love investigating the world around us. It is a fun way to gain interesting and useful knowledge.
This video involves the response of a Mabato inflatable PVC punching bag from Walmart to changes in the atmosphere.
Let's get started. Key observations that stimulated the present investigation are shown in the slide. The photographic evidence was obtained with an Apple iPhone. Practically anyone could make the same observations and obtain the same data. No special tools are needed here.
One day in December 2020, just as Anna was starting e-learning for the day, I noticed that our punching bag on the back porch looked like a wilted flower. This was a change from the previous evening. Later that morning, though, the bag looked normal again. Next day, we noticed that the bag had wilted again, so we took some pictures. The first picture was taken at 8 a.m. It was chilly outside. The second picture was taken at 11:45 a.m., around the end of my lunch period. By this time, the punching bag was standing straight up again, repeating what had happened the day before. The air was quite warm by this time. A comparison of the pictures reveals the sun is higher in the sky at 11:45 than at 8 o'clock.
The next step in our investigation was to show our data in diagrams. We wanted to stress essential aspects of what we had found and focus our sight on them.
The punching bag has 3 inflatable compartments. The upper one is cylindrical. A corresponding reference axis is indicated in the diagram. The angle alpha can thus be used to indicate the extent of wilting with respect to an axis for the lower compartment. It is not the only approach to analysis here, just a convenient one.
We decided to do some research on the material properties of the bag. The product description on Walmart.com says it's made of PVC or polyvinyl chloride. This material is well known and has many practical uses. Different shapes can be made of PVC, including thin sheets, and sheets can be manufactured in different colors, including yellow and black. Could the material properties of PVC be responsible for the observed behavior of the punching bag?
The slide shows that N-chloroethene molecules combine to give a PVC polymer of N subunits. A molecular model of PVC is shown on the right. Each punching bag compartment contains a huge number of these molecules in a thin disordered pile, a sheet. Details of the chemistry and physics of PVC are interesting, but beyond the scope of the present video. What matters here is the stiffness of a PVC sheet will increase as the temperature decreases. This seems contrary to our evidence, which shows the punching bag wilting when cold.
What if a change in stiffness does not explain the observations? Maybe looking inside the bag will lead to insight, but there is nothing inside besides air. But air is not nothing. It comprises nitrogen, oxygen, argon, and carbon dioxide in different amounts. Nitrogen, oxygen, and carbon dioxide are molecules here. Argon in the atmosphere is found as individual atoms. Alphabetical symbols and models of these constituents of air are shown on the slide. Interesting? Yes. But does it explain anything here?
There is no need to mention carbon dioxide here. It accounts for less than 1 part in 100 of the composition of the atmosphere and can often be disregarded in analysis. We are not talking about a greenhouse effect here. The focus must be on what is essential to the matter at hand. Atmospheric pressure varies in time, as you can see from the data shown in the slide. Over a short time interval, however, a few hours, atmospheric pressure is often essentially constant, so we will treat it as constant.
Okay, we need a model of a gas that relates the temperature of the atmosphere to the volume of the punching bag. How about the ideal gas law? PV equals nRT.
No real gas is an ideal gas, and air is a real gas. Air particles occupy space, and they interact with each other in ways other than just colliding like billiard balls. That said, many gases show ideal gas-like behavior if the concentration is not too high, including air at atmospheric pressure. Note that according to the ideal gas law, the product of pressure and volume equals the product of the amount of gas, the ideal gas constant, and the temperature. Both sides of the equation have units of energy. If the amount of gas is fixed and the pressure is fixed, V over T will be constant. We can therefore expect V and T to change together.
Another model is useful for explanation here. It is a combination of the Boltzmann energy distribution and the kinetic theory of gases.
The graph on the upper right of the slide shows the molecular speed distribution of a gas obtained by combining these models. It is called the Maxwell-Boltzmann distribution. What's important here is that the most likely speed of the molecules increases as the temperature increases. The graphs will be roughly the same for argon and the molecules of interest here. The differences do not matter here.
We now have enough information to explain the punching bag's behavior. It wilts when surrounded by cool air and stands straight when surrounded by warm air. We neglect changes in atmospheric pressure and changes in temperature of the floor, which will be much slower than changes in the temperature of the air. When the surrounding air of the bag is warm and the gases inside the bag has the same temperature as the air, the molecules inside the bag will move at a higher speed and strike the wall of the bag at a higher speed, pushing the wall out against the surrounding air. When the surrounding air is cool, and the gases inside the bag is at the same temperature as the air, the molecules inside the bag will move at a lower speed. These molecules will still push the wall of the bag out against the surrounding air, but not as strongly.
The air inside the bag will cool down as the surrounding air cools down, and it will warm up as the surrounding air warms up. The ideal gas law suggests compartments of the bag will expand as the air warms and shrinks as the air cools, just like footballs, bike tires, and car tires. In fact, the ideal gas law predicts a volume increase of about 4%, or 1 part in 25, for a temperature rise from 60 degrees Fahrenheit to 80 degrees Fahrenheit under constant pressure. Just divide 300 by 289, the corresponding temperatures in degrees Kelvin, multiply the result by 100 to convert it to a percentage, and round the result to the nearest whole number. A 4% change in volume over 4 hours will be much larger than the corresponding change in pressure on a typical day of the year. For a cube, a 4% change in volume will correspond to a mere 1.3% increase in length, width, and height, about 1 part in 75 per side. Hard to detect by eye. Just find the cube root of 1.04. This change in inflation can make the punching bag wilt or stand up. All 3 compartments will shrink as the temperature decreases. The middle and lower ones bear the weight of the upper one. However, so they will deform under its weight. The upper one will not deform. It bears no load.
We have not done a detailed study of the punching bag. Still, we have enough information to give a rough prediction of how the angle alpha will vary with temperature.
How much the angle alpha will change will depend not only on the amount of temperature change, but also on the inflatedness of the compartments. If the lower compartments are fully inflated, they probably won't deform much over a modest temperature change. But if the lower compartments are not fully inflated, just nearly fully inflated, they will deform under the same temperature change. The same holds for automobile tires. Our punching bag can give a visual response to temperature change, but if an accurate measure of change is needed, get a good thermometer. Here is an analog. Wind chimes can give an audible response to wind speed change, but if an accurate reading of wind speed is needed, get a good anemometer. Still, the wilting punching bag is interesting, and attempting to explain it has provided much insight on the behavior of matter.
If we treated our results as preliminary data for a more thorough investigation, what would be different?
It would be better, actually, to measure alpha at several time points, not just 2 of them. This might require doing the experiment on a weekend instead of a school day. The temperature and pressure should be measured at each time point. This way, a more convincing exclusion of pressure from the explanation can be made. The general conclusion of the study will probably not differ from what we have found, though.
The world around us is fascinating. Explaining it can be difficult, but finding explanations is satisfying. The present video describes our quest to explain the unexpected behavior of our inflatable punching bag.
Searching for explanations can provide insight on nature, how the world is made and how it works. Explanations can lead to new inventions, ways of harnessing the properties of nature to do something useful. Keys to discovery are noticing something interesting or unusual, taking the time to investigate it, thinking in terms of details of the case at hand and general principles, and finding an explanation that makes sense from all angles.
This concludes today's video. If you liked it, give us a thumbs up. All of us a smile. For more videos like this, subscribe to this channel and hit the notification bell. See you next time. Bye!